Hi there, this is Dr. Hisham Said. In this video, we'll really think deeply about J. And J is a term we have in the shear stress formula from torque. And I know you might say, oh, J is the polar moment of inertia. I know that, but we want to really think about what is really J? What does it matter? And why it's so important actually in this formula. So we'll introduce J by comparison between two cases of shafts. They're fixed at one end. They both have L1 and L2 are equal. They have A1, A2, and they are subject to the same load. And what we're trying to do here, just to control here the comparison, is to say that A1 is equal to A2, L1 is equal to L2, and G1 is equal to G2. So it's the same cross-sectional area, not geometry, but area, the length, and the type of material, so the shear modulus here. One thing to note, in case 1, it's a solid shaft. Case 2, it's a hollow shaft. And the question here is, which shaft has the highest torsion resistance? And what do we mean here by torsion resistance? It's, if you think torsion resisting shear stresses from torsion, so tau is equal to T rho over J, and also resisting the tendency to twist because of that torque. So phi is equal to TL over J G. If we kind of put everything equal for both case 1 and case 2, you will find that J is really here the controlling factor. For the same length, for the same load, torque, for the same material, G, for the same cross-sectional area, A, J will be the controlling factor here, as all other factors are the same. So now the question is, which one has the highest J? Because if you look here, J has an inverse relation with both tau and phi. So if you want to have highest resistance to torsion, so you want to have the least tau and the least phi, which happen with the highest J. So the question turns out to be, which one has the highest J? So let's go to the basics of J, which is the polar moment of inertia. So it's the rho distance, the radius from the origin to any small dA, and you do the integration here. And if you look at the comparison between the two areas I have, the solid shaft and the hollow shaft, you can see here that for the same magnitude of the area, rho gets bigger, because now with the hole inside that cross section in the middle, to keep the same area, you have to keep a lot of the meat of the section, or the area of the section, away from the center or the centroid of the section. So what that results in generally larger or longer rho distances when you do the integration. So the second case, the hollow shaft, will have larger polar moment of inertia. So when you have larger polar moment of inertia, you will have least deformation or twisting, and you will have least stresses. So one thing to note here is that also tau increases with rho. So if you look at the tau equation, there is rho on the top of the equation here, so T rho over J. But yes, it's if you increase rho, if you increase the cross section, kind of get it away from the centroid. In case of the hollow, it's a first degree kind of relation, so it's to the power 1. But if you look at the J formula for a circular section, it's pi c to the power 4, so it's a 4th degree. And we know rho is a radius that ranges from 0 to c, so pi c to the power 4 over 2, now you're dealing with a 4th degree kind of relation. So we kind of J have 4 times the impact, reverse impact kind of on tau, versus the direct relation, which is a 1st degree between rho and tau. So yes, you increase the rho, it will increase also the tau, or the distance that is causing here the tau because of the torque T, but also that distance, that rho, helps in resisting the shear stresses developing from the torque. So I hope that helps in understanding really the impact and the contribution of J in both the shear stress and the twisting angle, and also helps to kind of understand and visualize what's really J. Thank you and take care.